Hi, and welcome to Geometry. This is from Illustrative Mathematics. We are in Unit 2 on congruence. And this is Lesson 3, Congruent Triangles, Part 1. By the end of the lesson, you should be able to say, I can explain why if all of the corresponding sides and angles of one triangle are congruent to another, then the two triangles are congruent. Previously, we've talked about if two triangles are congruent, then all of the corresponding parts of the two figures are congruent, CPCTC or CPCFC. Today we're going to take the converse of that and say, if all the corresponding parts are congruent, then the two triangles are congruent. So here I want you to name something that must be true, could possibly be true, and definitely would not be true about if triangle ABC is congruent to triangle A prime B prime C prime. And after you do this, you can listen to some of the responses that I got from students, which were that angle A has to be congruent to angle A prime, angle B has to be congruent to angle B prime, angle C has to be congruent to angle C prime, segment AB must be congruent to segment A prime B prime, segment BC must be congruent to segment B prime C prime, and segment AC must be congruent to segment A prime C prime. What could possibly be true? One of the angles could be a right angle, it could be a right angle, right triangle. One could be obtuse, it could be obtuse. Two of the angles could be congruent, or two of the sides, it could be isosceles. Or maybe none of the sides are congruent, and it would be a scalene triangle. Those are possible. Things that definitely could not be true. You could not have angle A not be congruent to angle A prime. You could have triangle ABC is a circle. If it's a circle, then it's not a triangle. So some things that are not true. So some things that you might have written down. When we mark this drawing, we're going to mark all of the parts that correspond with each other that are the same. So I'll start with this angle. There's one angle, it's the same as this one. This angle has to be the same. Angle B would be the same as B prime. And angle angle A would be the same as A. I'm also going to mark the sides. I'll mark them with a tick mark, this one with two tick marks, and this one with three tick marks. It makes what looks like a fuzzy face, if you want to think of it that way. This is all of the corresponding parts of the one triangle must be congruent to the other. And here is a Geogebra applet. If you open it, you can see these two triangles don't line up, but I can make them line up if I rotate this, and then if I reflect it, then I could translate it. And I want to point out to you that any two triangles that are congruent can be matched up to map one onto the other by doing a translation, a rotation, and a reflection. Now, you may not need all three of those transformations, but if you do a translation, a rotation, and a reflection, or some combination, they will always match up. So that's all that it takes to match up two triangles that are congruent. So invisible triangles is the game, and we played this together. We played it in partners, where one person, the objective is to use the language. So we're going to use the transformer person is the one that uses the language to tell what transformation to do. The other person, the player, then has the player card and tells what is congruent and can draw on the picture what the transformer tells it to do until the two match up. We did a practice round and we did 3 other rounds. I'm going to walk you through it. Instead of using the language here, I'm going to walk you through it using the GeoGebra. Because after we did the demo, now this is for the demo, to teach a demo, after we did the demonstration, where I started off by saying triangle JLK is congruent to triangle PRS. And I could have said J corresponds to angle P, angle L corresponds to angle R, angle K corresponds to angle Q. And then the person with the previous card, the transformer card, tells me what to do. So what it might look like is transform triangle JLK from point J to point P. If I do this, I'm going to create a translation from J to P. When we translate this, it ends up here. I'm going to change the color of this so that you can see this a little bit clearer. And change this color to orange. And now the next step would be to rotate rotate, because and I would tell if I had the player card, I would say point P correspond and point J prime are the same. J and P are at the same location. So the next transformation would be to rotate. Rotate, when we defined it, the person with the transformation card would say rotate around point P. And how many degrees are we going to go? We're going to go this many degrees. And I could measure that. I could construct the angles to measure this angle, because this is how far I'm going to go. It's going to be 30 degrees. So when I do the transformation, rotate it around this, I'm going to go 30 degrees. And I'm going to go clockwise. So the default is counterclockwise. I'll put a negative sign in front of it to make it counterclockwise. What is it I'm going to rotate? I'm going to rotate this figure. When we apply it, it ends up here, and I'll change the color on this again so that you can see it. And the final thing is to reflect this triangle across this line. So the person with the transformer card would say reflect triangle J double prime, L double prime, K double prime, or triangle JLK here. Reflect it across line PQ. And when we do that, when we apply that to this triangle, sure enough, wait a minute, I reflected across the wrong line. Let me go back. I'm going to define the transformation, reflection across this line. And when I reflect this triangle across this, there it ends up. Now it ends up in the right place. And we did this for each of these. And you should do this for each of these. If you're doing this on your own now because you missed class or whatever reason, what you can do is you can go to make sure that you are familiar with the language of the transformer card. When we translate, we're translating a triangle. So here, if I were to translate triangle ABC, I'm not going to go from B to D. Point B, 64 degrees, matches up with point E. So I could define the transformation. Define the translation as going from point B to point E. We're going to translate triangle ABC from point B to point E, and then it matches up. And you do this on each of these. There's actually 3 times that we did this. And I've given you the opportunity to do it in Desmos as well, so that you can try it on your own. And then for the synthesis, the goal of this was to get you to be confident in using the language of taking one triangle onto another, a congruent triangle, regardless of the starting orientation. And you can always do this with a translation, rotation, and a reflection. And you may not need all 3 of those, but you can always get one onto the other with a translation, rotation, and reflection. So maybe ask yourself what was difficult with the game. If you found it easy, what was your strategy to make it easy? And then you can try playing me, where you do I have the transformer card, and I don't look at you. And you would I would tell you what to do here. You would tell me that these 2 triangles, ABC, is congruent to DEF, and I would tell you how to do it. What I might say is to translate triangle. I'm going to translate, do form a translation from point D to point A. And I'm going to translate this triangle. I'm going to rotate it. How much do I need to rotate it? I need to measure the degrees, but it's going to be by this angle. I want this point to match up with that one. So it's going to be this angle. How many degrees is it? Let's see. It looks like it's 60 degrees. So I'm going to rotate, define the range, rotate around point A by 60 degrees. And it's going to be negative 60 because 60 would be in the counterclockwise position, and this is going in the, and this is going in the clockwise direction. And what is it I want to rotate? I want to rotate this right here. I rotate it, and there it is, and it matches up directly. So you see how this works. Why do they coincide? This is activity 3. This is the difficult one. This is where we do 3 reads is the routine. And you're going to see that by doing a translation, reflection, and a rotation, it'll always work that one triangle will match up with the other. And first I'm going to read it, then we're going to talk about the language. And I would read this aloud. I would say, Noah and Prior were playing invisible triangles. And For card B, for card 3, Priya told Noah that in triangles ABC and DEF, she named all of the congruent parts. Triangle ABC is congruent to triangle DEF. Here are the steps Noah told Priya to do to make sure all 3 vertices coincided. First was to translate triangle ABC by directed line segment from A to A to D. Second was to rotate the triangle A prime B prime C prime around point D so that rays A double prime B double prime matched up with D and E. And then when you reflect this A double prime B double prime C double prime here across line DE, then the 2 would match up. After those steps, the triangles are lined up perfectly. Now they are, and we would read this 3 times. The first time, and I explained why we would do it 3 times. The first time is to get a picture of what's going on. The second time is for the angle relationships. And the third time is to ask yourself, why does B double prime have to be at the same place as E? Anyway, we first translated by directed line segment here in the brown. Then we, so we got to A prime, B prime, C prime. Then we rotated by B prime, DE. And when we rotate it around this angle right here, we get to A double prime, B double prime, C double prime. And then we reflected it. Now the question is, let's see, answer their questions. So here's the questions. We know that ray A double prime, B double prime, and DE line up because we said they had to. When we rotated by this angle, so that they had to line up. Why do points B double prime and E have to align? So doing the angle is one thing to make sure it's on the same ray, but why does that point have to be at the same distance on that ray? And finally, when we reflect this blue triangle, A double prime, B double prime, C double prime, the image, which is the red, when we reflect it across the segment DE, the image is the red. How do we know that the image of ray A double prime, C double prime, the image which would be this red line, will line up with ray AF? And how do we know that points C double prime will match up with F? So there's 2 separate questions going on here. First of all, why does it end up on the same ray? And then why does it end up at the same distance? And I've put the answers down here below. And I want you to read these very carefully. I'm not going to read them here because they're very long, but I want you to try to understand what it is that I've written. I'm very precise with my language, and I think that you should be too. This is an understanding, and this is probably the most difficult day of what we'll be talking about in this class. The goal of the discussion was to make sure that you understand that we can be sure that all points and rays coincide after translating, rotating, and reflecting. Why does Noah say so that rays A double prime, B double prime line up with DE, rather than saying that segments A, B double prime, B double prime line up with and DE line up? When we're talking about the rays, that's because we did an angle transformation. Okay, here's why. 2 steps. There's 2 steps to the proof. First is to show that the angles get the rays to coincide, and the second is to say the distance, so that the points coincide that are on that ray. This should go to your reference chart. It is the converse of if 2 triangles are congruent, then their corresponding parts are congruent. Here we're saying if the corresponding parts of 2 triangles are congruent, then the triangles are congruent. So it's if this, then that. We changed it to if that, then this. If you didn't download the document, the reference document, reference chart, or you've lost yours, you can download it again, put it in a safe place, bring it to class every day. We will use this. You will fill it in as we go, and we will use the information on it throughout the entire geometry course. Now, reflecting on proof, here we have 2 triangles. All of these corresponding parts are congruent. Wait a minute. 1, 2, 3. There are only 3 that are listed that are congruent. What rigid transformation will take GBC onto triangle ABC? And then explain how you know that G prime, when it's reflected across this line, will land on A. Finally, is triangle GBC im.g.2.3.G.B.C. congruent to triangle ABC. So here's what we say. First of all, you're going to reflect it across line BC. Or you could reflect it across the perpendicular bisector of this segment. Second, reflection preserves an angle measure. So G prime will be on ray AB, because when you reflect it by this angle, it's going to be the same angle, which is going to be along this ray. And it says here, the reflection preserves length. So this distance will be the same distance here, so it's going to be on top of A. This is important. We get the angle first, so it's on the same ray, and we get the distance, so it's on the same point. And yes, there is a rigid motion that takes the one triangle to the other. It's a reflection. Here's the summary of the lesson. You can read this and explains about this. And finally, there is some sentence frames which you can use in proof. And this is an important page. You may want to copy it or copy this down, because these are the words that you can use when you're doing proof. And that's all I got for you today. Good luck and success.